Hello everyone, I'm Somesh. I work with the University of Malta. I will be presenting some works on the conic approximation methods for the optimal power flow operation. The agenda of this presentation will revolve around what optimal power flow is, why is relaxation of the optimal power flow important, and what are the OPF relaxation methods that are available with us, and some solutions and some results with those methods are also discussed. Now, we know that the optimal power flow is an important and a very powerful tool to have demand and supply balance while minimizing the costs and the loss of the system. They also are imperative in making many market decisions in a more decentralized market. And at the same time, we also know when we solve an ACOPF, we have several non-convex equalities and inequalities within the constraints. And that makes the OPF problem more difficult to solve using non-linear techniques. So that gives the impression that relaxation and linearization are important for solving ACOPF, especially when we go for more complex networks, such as either distribution networks or transmission networks, which are of a larger scale. So this is what an OPF looks like. We have a cost function, simple generation cost function, which is the quadratic cost function. We have to minimize that cost function based on these constraints. Some of them are equality constraints, some of them are inequality constraints, and the non-linearity comes from the voltage constraint, which is basically a phasor. So the voltage contains the magnitude as well as the angle, and the polynomial constraints, they come from the line flow limits. So this is where we have nonlinearity and non-convexity in the OPF formulation, the original OPF formulation. Now, if we wish to have better computational accuracy, we seek to generally linearize our OPF. One way is to use the DCOPF, but with the DCOPF we have one issue that we have flat voltage characteristics within the DCOPF, and when we solve a loss minimization, DCOPF for distribution network can not be very well suited. So we have several relaxation techniques. One is the semi-definite programming, the Lagrangian approximation. We chose the second order conic programming for our relaxation. So this is the partially relaxed OPF. We lift the terms to the rectangular levels. So when we lift the terms to rectangular levels, one good thing is that the polynomial equations are now gone. The sine and cosine terms are gone, so it is partially relaxed. But at the same time, if you see equation 3D, the equation non-convexity still is retained. So what happens is, since the non-convexity is retained and the angles are not recovered within the constraints, this is sometimes this gives not a very good solution when we especially do cost optimization in distribution networks. So we lift the constraints further up. We use conic terms. This is basically the conic relaxation of the OPF, in which we make an equation of a circle. If you see the variable CII, Cij and Sij, these are becoming an equation of a circle. So if we see from the point in a subspace, we see a cone. So that's why we call it as a conic relaxation. So we make cones in this thing. So reformulating the original OPF in the cone terms, we have successfully linearized the equations. But the only thing is that to have the equation of circle linearized, we further use the McCormick envelopes to make the equations fully linear. This way we achieve a better relaxed solution and without compromising the computational accuracy and the speed of the OPF solution. But conic relaxation also suffers with the angle recovery. So we add the angle-based constraint to have angles within the solution, not as a post-factor solution for the OPF. So, but the only problem with this thing is that the OPF problem becomes polynomial again. Now, coming to some base cases, we have compared our results with the MEDPOWER solver, and we see that we compare on the basis of the cost and the computation time. So, keeping the base of our solver as at 1 second or 1 per unit with the SOCP formulation, we see that we have good results and fast results with the help of the linear SOCP and the angular constraint based SOCP. But at the same time, we see that the branch and bound with the help of the partial relaxation takes too long because generally they are stuck to find a lower bound for the solution. Loss minimization is done with the help of the partial relaxation technique because the partial relaxation can have loss minimization as an objective. So we see that for the loads of 315 megawatt and 259 megawatt, we have somehow reduced the losses with the help of the partial relaxation technique. Same goes for the distribution network. We have considered 3 distribution networks for our studies. The IEEE 1822 and the 33 bus system. And the same thing we have used the same studies using MEDPOWER and with the help of SOCP and the angular and the non-angular conic programming, we have been able to find a solution within a good operational time, and at the same time they are in very good agreement with the IP-opt based results, and the optimality gap is also nearly 0. But the only problem is with the partial relaxation we are unable to find a solution for the distribution networks because of these sparsity of the Jacobi and the admittance bus that is formed. So going further up for the loss minimization, we have very minute loss minimization because this is a distribution network and we haven't considered any bidirectional power flows in case of our distribution network. So since it's a unidirectional current flow, the loss minimization is only limited to limiting the voltage bands of the network. So to conclude, we see that we have compared 3 approaches of the OPF problem: the nonlinear, the partially relaxed, and the conic OPF, and see that to have good agreement with the nonlinear OPF, we can use conic OPF with angular constraint, although it's polynomial, but we yield a very quick result with this thing. And loss minimization with the conic OPF is still an open problem, and we are looking to come up with a solution for this. Thanks.
Thank you.